Hello, discrete math fans. Let's check these quantified statements to see if they're true. For all x in the reals, x to the fourth is bigger than 0. For all y in the natural numbers, y has a prime divisor. For all m in the natural numbers, m squared is bigger than or equal to m. For all m in the real numbers, m squared is bigger than or equal to m. So the last two are slightly different. The predicate is the same, but the domain of the predicate variable is different. Okay, part A is false. The predicate x to the fourth is bigger than or equal to 0 is false when x is equal to 0. Take note, this is the only counterexample. Every other value of x that we plug in that's in the domain, that predicate is true. It only takes one counterexample to make it false. Okay, before we give the answer to B, I think we should say something about the language that's being used here. We're going to say that m is a divisor of n if n is divisible by m. For example, 7 is a divisor of 21. We can also say that 1 is a divisor of 5. A prime number is a non-zero integer, other than 1 and negative 1, whose only divisors are 1 and itself. So B is false because 1 is a counterexample. Now, we should note that 1 is not a prime number. You can win a bar bet out of this. You like to think that 1 satisfies the definition of the prime number, but in fact it is not. 1 is neither prime nor composite. It falls in its own category. So 1 itself does not have a prime divisor. C is true because if we square any positive integer, it's either going to produce the same number, if you plug in 1, or it's going to produce something larger, in the case of all larger positive integers. And then D is false. So D, we're allowed to plug in any real number, so when we plug in 1/2, we're going to get a counterexample. And there's many counterexamples for D. Okay, that's all for now.